now we have Nina Hernitschek that will tell us about point of interest. There we have it.
Okay.
Variables.
Now you can see my presentation? Yes.
We can. I will let you know when you have 2 minutes.
All right. Thank you. Today I will talk about our point of interest variable broker. We're caring about variable objects, especially our library stores, Cepheids, because they're easy to detect and they allow for a unique distance measurement. I was working a lot with our library stores, and this is why the idea of building this broker came up, and the detection of structure in a Milky Way, such as tidal streams and dwarf galaxies, is super easy when having our library stores at hand, and it will answer a lot of questions regarding the formation history of our Milky Way. So what are points of interest? These are especially dwarf galaxies and globular clusters and tidal streams with a lot of substructure within them. It's not going to, here you see one example for a tidal stream with a lot of substructure. This is a Sagittarius stream where I was working on. And what I needed often was getting updates on light curves, getting updates on light curve properties. And this will be much better when having a broker that delivers this automatically from LSST. It is important to fill in more and more data points when doing research on such objects in the Milky Way. And so the scientific goal is that the proposed alert broker should enable users to get update on variable star observations within such interesting regions. The interesting regions should be both predefined, such as known stellar streams, dwarf galaxies, globular clusters. And the list of predefined objects is frequently updated from publications, and it should be also user created. For example, a user might only want to get updates on a specific part of a stream or of a globular cluster. The scientific goals are to add value to 2 of the 4 science pillars of specified for LSST. So for exploring the transient optical sky and as a result for mapping the Milky Way. So this image depicts this quite good. We started out with the light curves to do science on Milky Way substructure, and a large and deep set of such variable stars can be explored by using LSST because it's going at least 2 magnitudes deeper than PanSTARRS 1. PanSTARRS 1 was the survey I was working mostly with. The anticipated output of the broker are the light curves itself of our library and Cepheids. They will be classified within the broker, within specific regions of interest as chosen by the user, and value-added information should be provided, such as periods, phase offsets. This is important as astronomers are usually working with precise light curve information from variable stars, such as fitted periods, to determine distance, and also to use phases at given timestamps. This application might sound a bit uncommon, but I've used it recently for precisely timing spectroscopic observations as follow-up studies for photometric surveys, such as PS1 has no spectroscopy, but I was using follow-up to complement it with spectroscopic information. Such value-added information can also be very specific on the object type. For example, our libraries showing a modulation and a pulsation phase or amplitude that is known as the Glasgow effect. This can be added to an object already identified as an library previously or by the classifier. Here, LSST's high cadence will provide better features. Now, features can be calculated that were not available from PS1 just because of the cadence. So we will do also a lot of cross matches. Cross matches will be done, for example, with variable stars catalogs already existing, such as a PS1 sample of our library catalog. This can be used as early as LSST gets operational. And then a classification itself will be built in the variable stars broker. This can be used as soon as a light curve quality is sufficient for doing the classification process. This means also to reclassify stars that were already found by, for example, PS1, so to do some kind of a catalog cleaning. You see here really a tree of variable groups, classes, and types. So how deep we can go into that tree just depends on what users want, what are our computing capacities, and how good the like curves are indeed. The user access should be simple and straightforward using a website, as shown here in the pictogram, for retrieving data using a simple graphical user interface or an SQL-like data query language. Tables should be downloadable as well as can be viewed online, and like curve features can also be downloaded. Prototyped algorithms already existing are used in a wide range of papers by us or papers by other teams. We have also tested some algorithms on simulated LSST data for eclipsing binaries or library stores and Cepheids. So here you see just one example on what can be done with even very sparse like curves, such as from a PS1. We can do, for example, a general fit of a like curve, delivering information that can be used for classification, as well as we can do template fitting for precise periods and phases. With LSST, this will become easier, but in the beginning of LSST, we might have to rely on such classification algorithms that are more computationally intensive and are built for sparse like curve data. So our experience mostly comes from the Data Science Institute at Vanderbilt University, where we are doing a lot of research regarding data science, machine learning, and in general data processing. And of course, also our strong astronomical background. So we are three people from Vanderbilt University, all of us working in astronomy and data science. So this is what I can say right now as a summary. Our algorithms are prototyped. Broker is not public available right now. As a summary, I can say what have we learned from previous surveys we worked on. We have mostly learned that sparse surveys can allow for the classification, but things can become rather tricky, and we hope that it works much better with LSST, so we can use faster and more advanced algorithms. Technical challenges we are looking for solutions right now is to do a fast feature extraction that works for almost all like curves. So we are already using the prototype multiband structure function, and we also look deeper into using template fitting for more variable classes. So I will end here, and I hope we have a bit of time for questions right now.
Yes, thank you, Nina. We have quite a few questions, and we have time for a couple of them, I hope, depending on the length. So, Guy.
Yeah, so I'm going in order of appearance. I'm monitoring both Slack and the Zoom chat. The first one comes from Rahul Biswas. Are you planning on doing this closer to the Milky Way or in the entire LSST footprint?
We're doing this in specific regions as far as they're chosen by the user, as they're defined by them, or objects within the Milky Way we already put in the broker, such as the known streams. So for example, Sagittarius stream has quite a distance to the Milky Way center, so we're really looking for shallow objects in the outskirts of the Milky Way to explore, especially the halo substructure.
Thank you. We have time for one more question.
Okay, from Paula Sanchez Saez, are you considering to include other classes of variable stars?
Yes, we try to include as many classes of variable stars as is possible from the data set given. So I quickly showed this variable star type tree. So of course we cannot cover the complete tree, but for sure we will do more than just only distinguishing between Cepheids or Lyrae stars and something else. So we will do, of course, subclasses such as or B stars or C stars, eclipsing binaries, stuff like that.
Thank you, Nina. So I invite you to check the Slack because it's being populated with questions for you.